Greetings! Today we continue our adventure with U substitution for integration, and honestly, this lesson is going to be exactly the same as the last one, except we're going to be doing definite integrals instead of indefinite integrals, and really, that only introduces one additional step if you want it. I think it's easier, and that's why I'm going to take the time to step you through it. All right, so let's just do this first integral that I have here. All right, it says consider the following definite integral. All right, and I notice that, right, it's the integral of a product. I can't just distribute that x in so easily. Oh no, there's no product rule for integrals. Let's try a u sub. And so I notice that I've got this x squared hanging out here, right? And so this x, well, he is at least of the right order to be x squared's derivative. So that informs my choice for what u should be. So I'm going to go ahead and let u equal x squared plus 1. No reason not to lump the 1 in there with it. All right. And then we'll go ahead and get the derivative of u with respect to x, because we're pretty sure we see u's derivative hanging around. So the derivative of u with respect to x would technically be 2x, and we'll start rewriting. We'll see what we need. Okay, so when we rewrite, I'm going to have from 0 to 1. Let's see, instead of writing x squared plus 1, I can just write u. That takes care of this, and then by cubing it, I will take care of the cube. Okay, and it looks like I still need to get in an x and a dx. So I'm going to come back to my definition of du dx and do a little bit of manipulation there, just as we've been doing this whole time. Right? By multiplying both sides by dx, I get that du is 2x dx. Well, I don't need to get a 2x dx in there. I just need x dx. So I'll divide both sides by 2 to get exactly what I want, right? So it looks like by writing du over 2, that will be exactly equivalent to x dx. So let's throw that in there. Du over 2, and that takes care of the x and the dx. Okay, and then we recognize that division by 2 is just multiplication by 1/2, so I'll bring that scalar multiple out to the front. And now I'm just looking at u cubed du, and it doesn't get much easier than that. All right, so we'll just use a little reverse power rule here. I'll keep the 1/2 out in front, and then u cubed will integrate to u to the 4th over 4, and we'll evaluate that between 0 and 1. Now here is where we need to pause, because this 0 and this 1, I'm just going to switch colors here for a minute. All right, this 0 and this 1, these are x values. And that's a bit of a problem because I have a u in here. So it would not make very much sense for me to go ahead and plug 1 in for u and 0 in for u when 1 and 0 are x values. So here's where you're going to get a couple of options, all right? The first option is that you can do what we would normally do and just back substitute, right? Change your u's back to x's, all right? And we would do that by letting u go back to x squared plus 1. So that's what we're going to do first, all right? So I'm going to do that work in green. All right, so I'll have the 1/2, and then instead of writing u to the 4th, I'll write x squared plus 1 to the 4th over 4, and I will evaluate that between 0 and 1. All right, and so let's expand that. All right, And I'm actually going to distribute the 1/2 in just to make the expanding a little bit cleaner. So that will give me x squared plus 1 to the 4th over 8, evaluated between 0 and 1. And then we'll come down here, we will evaluate this thing at 1, and we'll subtract this thing evaluated at 0. So when x is equal to 1, I have 1 plus 1, which is 2. 2 to the 4th is, all right, I'll just write this down, right? 16 over 8. And then when x is 0, I'm going to get 1 to the 4th over 8. All right, so ultimately, I will be left with, well, 16 over 8, that's just 2 minus 1/8. And at the end of the day, I'm just going to call that 1 7/8. So that's one way to do it, all right? We just did what we normally do. We change our u's back to x's and call it a day, all right? However, if you notice, the expression with the x's is a little bit more complicated than the expression with the u's. And I'm always trying to think, how can I be lazy and save myself some time? And the answer is that you can always be lazy as long as you're willing to do a little bit of thinking, all right? So, all right, I think to myself, what if I didn't want to back substitute with the x's? Well, then I would just have to make sure that my limits of integration were no longer x values, but were instead u values. And changing those numbers is going to hinge on this definition right here. All right, so let's take a look at this limit of integration right here, when x is equal to 0. That, by the way, is a poorly drawn arrow. All right, when x is equal to 0, if I go back to my definition of u right up here, when x is 0, u will be equal to 1. And when x is equal to 1, let's see, well, based on our definition of u will be 1 squared plus 1, 2. So by simply converting our limits of integration from x values to their corresponding u values, we can get around all of this back substitution. So let's go ahead and do that. All right, so I'm just going to rewrite this over here. All right, I'll leave it as a u to the 4th over 4, but I will now rewrite it with my limits of integration as from 1 to 2. So now I've got u as my variable and u values as my limits of integration. Everything agrees, and we like that. All right, so now let's finish this problem out down here. Again, I'm going to distribute the 1/2 in just to make it a little cleaner. All right, so that will actually be u to the 4th over 8 evaluated between 1 and 2. And then when we expand that, 2 to the 4th is 16 over 8 minus 1 to the 4th is 1 over 8. And okay, we can already see things are moving in the right direction because we will get 2 minus 1/8, and that will give us 1 7/8. So you should get the answer, the same answer, either way. Okay, so if you'll go down here, right, you'll see your two options, right? You can do what we did in the green, which was back substitute with x's. In your original expression. So convert all of your u's back to x's. Or you can instead change your limits of integration to u values. At first, you might be tempted to always go with option 1. You'll quickly realize, though, that option 2 will more often than not save you some time and hair pulling. You'll also be less likely to make a careless arithmetic mistake when the actual expression is less complicated. So that's what we're going to practice today. I'm going to take you through a couple simple examples and we're going to call it a day. All right, alrighty. So we've got a pretty simple case of U substitution here. Just going to zoom in a little bit. All right. So I take a look at this and I think, all right, I think I see the function derivative pattern here. All right, I see that, well, I've got an x cubed, so I might as well lump in x cubed plus 1, which would mean that this x squared term, okay, x squared, you're the derivative of things that are cubed, so this looks good. All right, so let's go ahead. We will let u equal x cubed plus 1, and then we will go ahead and get the derivative of u with respect to x, which, based on our definition, would be 3x squared. And then we can start to rewrite. Okay? So, first thing that I'm going to do, actually, all right, so I'm going to write my definite integral. I'm also going to take this 2 that's right here and say, 2, you're a scalar multiple, so there's no reason you can't come right out to the front here, taken care of. All right, instead of writing the square root of x cubed plus 1, I'm just going to write the square root of u. And so that takes care of x cubed plus 1. It also takes care of the radical. And now let's see, I just need an x squared and a dx. And of course, getting those in there is going to come from this relationship right here. So let's just do a little bit of algebra and see what we can get. I'll multiply both sides by just by dx, and I'll get that du equals 3x squared times dx. And I look back at my expression and I say, oh geez, I don't want 3x squared dx. I just need to get in an x squared and a dx. And of course, that's as simple as just dividing both sides by 3. And so then away you go. And yay, du over 3 is exactly equal to x squared dx. Let's write it in. Du over 3, and that takes care of x squared and dx. Now notice, I did not write my limits of integration yet, because I'm going to change them to u values right away, because you will forget. I know, you just want to get on with the problem, but my recommendation is do it now, because by the time you're done with the actual integration, you'll feel so accomplished, you'll forget. All right, so based on this definition, this relationship between u and x, when x is equal to 1, u will be equal to 1 cubed plus 1. Okay, that's 2. And then when x is equal to 2, u will be 2 cubed plus 1. That's 8 plus 1, which is 9. All right, so those are our new limits of integration, and we can proceed with the problem as normal. I'm going to factor out that over 3, one less thing to deal with. So I will end up with a 2/3 in front. I will still have my from 2 to 9. I'll think of root u as u to the 1/2, and then this is just peachy. All right, so we'll come down here. All right, so when we undifferentiate, well, I'll keep the 2/3 out in front. U to the 1/2, when I reverse power rule, will become u to the 3/2 over 3/2, which actually means times 2/3. Oh, we were so close to having those cancel. Oh well. All right, and then evaluated between 2 and 9. Okay, I will go ahead and distribute this 2/3 in. I just don't want to have to, I don't want to forget about it. I don't want it to get away from me. So that will actually be 4 over 9 u to the 3 halves evaluated between 2 and 9, and then we can go ahead and expand that. Okay, so the value of this function at 9, well, the 4/9 is going to stick around, 9 to the 3 halves. That really means the square root of 9 cubed. So the square root of 9 is 3, and 3 cubed is 27. Minus the value of this thing at 2. All right, so again, the 4/9 is going to hang around. And then 2 to the 3 halves will really mean, all right, the square root of 2 cubed. All right, and so, let's see, do I want to write that differently? The square root of 2 cubed. Maybe I'll just write that as 2 root 2. And then we'll tidy this up a little bit. All right, so, well, in this expression right here, the 9 and the 27 will cancel to just become 4 times 3. So that will be 12, and then minus, let's see, well, 4 times 2 root 2 over 9. I don't think that's going to get much prettier than 8 root 2 over 9, and there's no reason for us to leave it any differently than this. Please check my arithmetic. It's been a long day. But hopefully you get the idea, right? The major step for this problem was simply changing our limits of integration so that when we got to the definite integral step, we didn't even have to think. Okay? Let's try the next one. Ooh, trig. All right. So, the question is, do I see a function derivative pattern? And I do, but be careful here, all right? Because I see that, right, if I choose my function as x squared, his derivative is there one way or another, right? X, you're of the right order to be the derivative of x squared. However, if I choose u as sine x squared, now my derivative that I'm looking for needs to have a cosine something, and I don't see that. All right, so the question is, whose derivative do we see? X squared. So that's our u. Okay, and then we can pretty much proceed as normal, right? So du dx is 2x, and we will start rewriting. All right, so my integral, let's see, instead of writing sine x squared, I can now write sine u. So sine of u, that takes care of the sine part, that takes care of the x squared. Now I just need to squeeze in an x dx. So if I come over here, du is equal to 2x dx. And while I don't need the 2 in there, I just want to swap in something that's equivalent to x dx. So we will divide both sides by 2, and that'll do it, right? Du is exactly equivalent to x dx. I'm sorry, or du over 2. All right, so by writing du over 2, I've gotten this guy, and let me change my limits of integration now before I forget. All right, so going back to our relationship between u and x, all right, well, when x is 0, u is going to be 0 squared, which is, ooh, yay, still 0. Cool. All right, so now when x is pi, u will be pi squared. That's fine. Just leave it. We'll take care of it. All right, and now we're good to move on. All right, I will now factor out the over 2 as a times 1/2 out in front, and then proceed as normal. Okay, and so now I can undifferentiate, and the 1/2 will stay in front, and then the antiderivative of sine will have to be negative cosine? Yeah, negative cosine u evaluated between 0 and pi squared. I'll distribute the 1/2 in just to make my evaluating easier. I don't want to forget about it. And then I will do the definite integral, right, from 0 to pi squared. Okay, so let's see. For our first term, we'll have negative 1/2 times the cosine of pi squared. Be careful, that's the cosine of pi squared, not cosine of pi squared, okay? And then minus negative 1/2 times the cosine of 0. And now I don't have my calculator on me. Normally I would take this piece to a decimal approximation, but for now I'm going to write it as is in exact form because I don't know what that number is. So that's negative 1/2 cosine of pi squared. And now the cosine of 0 is 1, but you knew that, okay? Cosine of 0 is 1, so at the end of the day, I'll be doing minus negative 1/2 times 1, so minus negative 1/2, so plus 1/2. And that should do it. That's not too bad, right? Okay, next page. In this part, I want to show you that there are actually multiple ways that you could choose u in a couple different scenarios, and it'll all still work out okay. All right. So you'll notice in example 3 that I don't see that function derivative pattern that I would be hoping for. But we learned how to handle this last time, right? I'm like, well, if I let u equal 2x, my derivative should be 2, and, well, that doesn't work. And, if I let u equal x, my derivative should be 1, and then, well, that's not working either. So I don't see the function derivative pattern, but we know how to deal with that, right? And so you pick something, right? Usually grouping symbols, such as a radical, are a good indicator for how to pick. All right, so for now, let's let u equal 2x minus 1. We will see where this takes us. Okay, so the derivative of u with respect to x is just plain old 2. All right, and then we'll start to rewrite. So here's my integral. All right, I don't know what to do with the numerator yet, so I'm going to leave it alone. I do know what to do with the denominator, so let's handle that. Okay, by writing root u, I've taken care of the radical, and I've taken care of the 2x minus 1. All right, I need an x dx, and I don't think that I'm going to get an x from this, but I can get a dx, so let's go get it, right? Du will be 2 dx, and well, I don't need 2 dx, I just need a dx, so I'll divide out the 2. Great. Du over 2 will give us dx. So that's taken care of. Now x. All right. Well, remember, if you remember from the last video, right, when we don't see that function derivative pattern, we can just go back to our definition of u right here and manipulate that until we get what we want. All right, so adding 1 to both sides will give us u plus 1 equals 2x. All right, and then I'll just divide both sides by 2 and find that x is equal to u plus 1 over 2. All right, and just so that my integral doesn't get very cluttered, I'm going to put that on over here, right? Putting something in the numerator versus putting something to the side along the fraction bar, it's the same thing, right? So I can just do u plus 1 over 2 out here and then just pop a 1 write on there to remind myself that it's not a 0. And then let me go ahead and change my limits of integration right now before I forget. So when x is 1, using this relationship right here, I can see that when x is 1, u is going to be, also 1. Fun. Then when x is 5, let's see, u will be 2 times 5 minus 1, 9. Okay, so now we're good to go. Let's clean this up, and let's clean this up quite a bit. I've got over 2 over 2, so really that's over 4. So I'll pull out a scalar multiple of 1/4. My limits of integration are still 1 to 9. All right. Then I will be left with u plus 1 over root u, which I am going to write as u to the 1/2 at the moment. Because, right, if we do that, we recognize a little bit more easily that I have an STD. Yeah, that sentence is all about context. So let's use that, all right? And we will get, right, well, u over u to the 1/2 gives me u to the 1/2. And then 1 over u to the 1/2 becomes u to the negative 1/2 du. And now we can undifferentiate. All right, so the 1/4 is still out there. I will evaluate this between 1 and 9 eventually. And let's see, u to the 1/2 will undifferentiate to u to the 3/2 over 3/2, so times 2/3, plus u to the negative 1/2 will undifferentiate to u to the positive 1/2 over 1/2, so that's going to be times 2 over 1. All right, and so again, I'm going to distribute in the 1/4. You don't have to do this every time. I just find it's easier. I'm less likely to forget about stuff. So let's see, when we do that, that will give us, let's see, 1/4 times 2/3 is going to be 1/6. And then u to the 3/2 plus, let's see, 1/2 u to the 1/2. And that will expand to, between 1 and 9, of course. All right, and let's see, that'll give us, well, 1/6 and then 9 to the 3/2. All right, well, that means the square root of 9 cubed, so 3 cubed, which is 27, plus 1/2 times u to the 1/2, so 1/2 times 9 to the 1/2, which is just 3. And then minus 1/6, and then, well, 1 to the anything is just 1, which is nice. So 1/6 times 1 plus 1/2 times 1, and I am out of room. I'm going to try to squeeze in a little bit of arithmetic here. I'll do it in a different color. Hopefully you've budgeted better than I have. So let's see, 27 over 6. Well, I can divide everything by 3, so that'll be 9 over 2 plus 3 over 2. Okay, so 9 over 2 plus 3 over 2 is 12 over 2, which is actually just 6. And then let's see, 1/6 plus 1/2, well, that's really 1/6 plus 3/6, so that's 4/6, right? So that 4/6 is going to be 2/3. So 6 minus 2/3 will give us a grand total of 5 1/3. Again, please check my arithmetic. My arithmetic is going to be the weakest part of this video. All right. Now, what I would like to do at this point, and this will really be the test here, is do this same problem again with a different definition of u. And if I've done all my arithmetic correctly, I should get the same answer. So cross your fingers for me, kids. Here we go. All right. Initially, this way is going to be a little bit more difficult up front, and then it's going to get really easy. So, and again, you might not think to do this, you might not want to do this, but I'm just showing you that you do have options when you don't see this, function derivative pattern that we're always looking for. So I'm going to go ahead, I'm going to actually let u equal this whole thing, 2x minus 1. Bam. All right, now, getting the derivative of u with respect to x is now all of a sudden more complicated, but it pays dividends later. So let's do it. The derivative of u with respect to x is, well, the derivative of radical anything is 1 over 2 root anything, and then chain rule, right? Derivative of the inside function is 2. And that's kind of convenient because the 2's cancel. All right, so just to save myself some room, because apparently I'm bad at budgeting that, I'm going to go ahead and erase the 2's because they cancel. All right, so now let me start to rewrite, and we'll see what I need. Okay, we'll sort of see where this takes us. All right. Okay, so we'll throw down the integral. All right, I don't know about the x up top just yet, but I do know that my bottom, just by writing the letter u, I scoop up the radical and the 2x minus 1. So that's all taken care of, and that's fantastic. All right, now I gotta get a dx in there somehow. Okay, well, we usually get that from this definition over here. So let's go ahead and do a little bit of algebra. All right, I'm just going to cross multiply to solve for dx ultimately, right? Because if I multiply both sides by dx, I'll get a dx over here. And then if I multiply both sides by root 2x minus 1, that will show up right here. Right? When I cross multiply, yes, that is all correct. All right, and now this is exactly equal to dx. We don't love it right now, but that's okay because we will fix it. All right, so we'll go ahead, we'll write it in. All right, so dx is exactly equal to du times root 2x minus 1, taken care of. All right, so now we just got to get the x in there somehow. And again, that will come from manipulating this guy right here. All right, so in order to solve for x in that expression, I need to square both sides. So that'll give me u squared equals 2x minus 1. And then when I continue to solve, I'll get that u squared plus 1 is 2x. Therefore, x is equal to u squared plus 1 over 2. All right, and because x is equal to this fraction, just so that I don't get my integral all confused, I will write that over here. U squared plus 1 over 2. And so now, by writing that expression, I've taken care of the x, and so I'll just put a 1 up here, and then before I forget, I am going to change my limits of integration from x values to u values. So when x is 1, I get the square root of 2 minus 1, so the square root of 1, that's 1. And then when x is 5, well, u will be equal to the square root of 2 times 5 minus 1, So the square root of 10 minus 1, which is the square root of 9, which is 3. Okay, and so now we've got something. And hopefully you are not entirely happy with it, because I am not entirely happy with it. And this is when I wish I were in the classroom with you guys instead, because I'd say why, and I know you'd be right there with me. But it's this. We want all u's. I mean, we went to all of this trouble to get u's in there, du's in there, u's in our limits of integration, and now there are x's messing it up. However, notice the offending item. We can replace it with some u's now, can't we? Yeah, apparently that root 2x minus 1, that's just u. So let's write it. Okay, so let's do from 1 to 3. We'll have 1 over u du. Now, instead of my root 2x minus 1, I can just write a u. And then the rest of it. U squared plus 1 over 2, and oh my goodness, we will so clean this up. All right, the first thing that I notice is that these guys cancel. And how nice is that? Okay? And so I guess the next thing I'll do is just bring the over 2 out to the front, so times 1/2. Then from 1 to 3, let's see, what am I left with? U squared plus 1 du. And that's pretty easy to integrate. I can totally do that. All right, so let's. All right, well, the 1/2, u stay. And then the antiderivative of u squared is u cubed over 3. The antiderivative of 1 is u. And we'll evaluate this between 1 and 3. I will distribute the 1/2 in, just to make my life easier. So that'll be u cubed over 6 plus u over 2, evaluated between 1 and 3. And just like in the last problem, I am running out of room, but I'm going to do my best. All right, so let's see. This expands too. All right, well, when u is 3, I'm going to get 27 over 6 plus 3/2 minus 1/6 plus 1/2. This is looking awfully familiar now, isn't it? I'm actually going to start working around this way. 27 over 6, that reduces to, again, 9 over 2. So I still am going to get 12/2, which is 6, minus, what did we say 1/6 plus 1/2 was? That worked out to be 2/3. Well, again, if that arithmetic is correct, we get 5 1/3, which, happy day, is the same thing that we got before. And so you can hopefully see that, there are many correct paths, and as long as your calculus is sound, right, and your substitutions are sound and your arithmetic is sound, at the end of the day, all roads lead to Rome. Now, I won't see you until Monday, so please, please, please let me know if you have any questions before this gets too far away from us. Good luck with your homework.